lesson, following the design of a cold room refrigeration system described in the previous module, our focus will be on ensuring its effective operations. Specifically, the system must maintain the appropriate conditions, temperature and time to prevent safety issues while preserving food. The refrigeration system based on a vapor compression system requires electric power to run the compressor. In particular, the power required depends on both the heat transfer rate removed by the evaporator and the efficiency of the cycle, according to the following equation. The big question now is, how can we ensure to continuously supply this power? The easiest answer is by plugging the compressor in the plug, taking advantage of the electricity provided by the grid. However, in our case, this path cannot be followed. Hence, alternative ways must be identified as no grid is available nearby the farm. We have to identify a solution that consists in a so-called off-grid configuration. The most common approach consists of powering the compressor through a fossil fuel power unit. However, some issues arise while deploying this configuration. From a logistic point of view, the fuel has to be available nearby the farm, and if it is available, it has to be moved to the farm to feed the power unit. Additionally, from an environmental point of view, this may result in a high environmental impact due to combustion emissions. Hence, we need to identify another technology to be deployed, being at the same time off-grid and more environmentally friendly. A reasonable and viable option is to generate the required power deploying photovoltaic PV panels and batteries. PV modules will produce the required electrical energy converting solar energy, whereas the batteries are necessary to guarantee stability to the system and to provide the required energy during both night times and cloudy days. Eventually, it can be mentioned that the refrigeration system can be modified selecting an absorption refrigeration system, which operates using mostly thermal power. In this configuration, the thermal power required can be produced by the combustion of biomass available nearby the farm. However, this solution, even though theoretically feasible, would require a less conventional and a more specialized technology. Since absorption technology is less widespread, it doesn't have the high volumes of vapor compression technology, making spare parts and related components harder to find. Additionally, more highly skilled personnel are required because the working fluid is toxic, ammonia. Therefore, alternative 3 is the one we selected to build our pilot plant. Coming back to design of the refrigeration system, the compression power was previously computed, but how many PV modules have to be installed? Starting from the data available, electric power required for cooling 280 watts, time required for cooling 12 hours, electric power required for temperature maintenance 160 watts, time required for temperature maintenance 12 hours, we have to compute the energy required according to the following equation, resulting equal to 5,280 watt-hours per day. Using the online available tool on Solar Atlas website, typing the farm coordinates as location of our analysis, choosing small residential SPV system configuration and modifying the parameters as deemed necessary, perhaps tilt of PV panels at least 5 degrees to guarantee modules cleaning during rainy days, it is possible to calculate the average energy provided per kilowatt of power installed for every month. Clicking on Open Detail, it is possible to see the complete analysis. Between all the months, the worst case has to be selected, corresponding to 98 kWh per month per kilowatt installed, corresponding to an average daily production of 3,267 watt-hours per day per kilowatt installed. Dividing the energy required by the produced one, we obtain the value of the power that has to be installed of 1.6 kilowatt. Considering an average power produced per module of 0.4 kilowatt, we obtain that at least 4 PV modules are required. Also, batteries are necessary, as already mentioned, but how to size the batteries? Selecting the worst month, same as for the PV, We report the data of the average energy provided per kilowatt of power installed on an hourly basis in a separate spreadsheet file. We multiply by the power installed, 1.6, obtaining the hourly energy produced by the field that we lower by subtracting the energy required, which is known. At this point, the cumulative hourly energy is computed, and then, finding the minimum and the maximum, it is possible to size the battery. Specifically, to this case, a battery of minimum 3.1 kWh is required, ideal case. However, when designing the battery storage, it has to be considered that energy might be needed during consecutive bad weather days. Here, 3 days are assumed. Then, a capacity of 15 kWh must be planned for. Hence, the PV field has to be increased of a plus 50%, which is a common practice, adding to 2.4 kW of power installed, corresponding to 6 PV modules. Eventually, increasing safety adds to costs increase. Hence, the identification of a trade-off is necessary. So, this is how to size a PV and battery field to ensure effective operations of a cold room.